Welcome to this video on entropy and the second law of thermodynamics. In this video, we're going to be taking a look at how the entropy of a system always increases. And I'm going to show mathematically that this is the case with some pretty simple math. So let's jump right in and make sure that we all understand that for an irreversible process, the entropy of the system, SF, the final entropy, will always be greater than the initial entropy. Now keep in mind that this is for the entire system and not for an individual object within the system. We also want to state that for a reversible system, the entropy could stay the same for the system. But one thing to note, and that you will see here, is that the entropy will never decrease for the system in any spontaneous process. So let's start with this example where we have this block at a temperature of T1 and this block on the right at a temperature of T2. And for my example here, I'm going to tell you that T1 is greater than T2. Now we know that if I put these in contact with one another in a closed system, what will end up happening is that heat will flow towards T2. So the heat lost, negative Q, by T1 will be exactly the same as the heat gained by T2, it's positive Q. Now eventually over time what we will note is that T1 will reach a final temperature of Tf and T2 will reach the same final temperature, Tf, and this will be when the blocks are considered to be at thermal equilibrium, and at that point the heat flow will cease. And so there will be no more heat movement between T1 and T2. Now, just to put a little side note here, if I then separated the two blocks once they'd reached the Tf final temperature each, they would not spontaneously go back to, say, T2 and T1. They would now be considered to have undergone an irreversible process. And so what we want to show here is that after this exchange of heat, the entropy of the system is going to be bigger than it was to begin with. So let's show how the entropy change of each object looks in terms of Q and the temperatures that they reach. And so what I'm going to show here is that the change in entropy for the hot object, if you will, is going to be equal to the heat that it lost over the exchange divided by the average temperature that it had over the change from T1 to Tf. So let's figure out what that average temperature Th is. So Th is going to be the change from T1 to Tf, and it's the average of those two. So I'm going to put T1 plus Tf divided by 2, just to give me the value for the average temperature that it was at as it changed from T1 to Tf. Negative Q is the amount of heat loss, and delta S sub H is the entropy of the hot object that I'm going to call the hot object, the entropy change of just that object. So let's do the same over here. First we'll calculate T cold, which is going to be T2 plus Tf divided by 2. So that's the average temperature as T2 went to Tf, and that's being named T cold. And the entropy change of just the cold object is going to be the same amount of Q here, but positive because it's gaining the heat, divided by its average temperature as they changed from one to the other. Now if we want to write the entropy of the system here, the entropy change for the entire system, which I'm subscripting S with S, is going to be equal to the change in the entropy of the hot object plus the change in the entropy of the cold object. And what we're going to do now is expand this to take a look at what's actually going to be happening. So if I put in delta SH here, I have negative Q over TH. So I'm just substituting these two expressions in. This one's Q over TC. And what I see here is that TC is going to be a value that's always smaller than TH. And this goes back to this original statement that I made that T1 was greater than T2, which means that TH will always have to be greater than TC. And you can look at that from the two calculations of how I got TH and TC and see that if they reach the same final temperature, they're both being divided by 2. If T1 was bigger than T2, then TH must be bigger than TC. So at this point, what we can see is that if we're dividing the same value Q by a smaller number here, the entropy change of this cold object is always going to be bigger than the entropy change of the hot object. And that is going to imply that delta S for the system will always have to be a larger number. And I'm going to show that with some example calculations here in a minute. So one thing that I'm going to do next is actually expand delta S for the system to represent the final entropy for the system minus the initial entropy for the system. And what I'll show here is that I'm going to calculate 4 SFS, so the final entropy for the system. So if I kind of move up here, I'm going to say that the final entropy for the system would equal, so I'm going to add the initial entropy for the system to both sides. So I'll have negative Q or minus Q over TH plus Q over TC. Now at this point, if you wanted to calculate some values here, you could just make up some numbers and see that this number over here, the positive entropy change of the cold object, is always going to be a bigger number than this number over here. And that means that SFS will always end up being bigger than S initial of the system. So let's plug in some numbers here and take a look at how that would come out. So I'm going to make up some values, and just to keep in mind, these values are kind of ridiculous. These are not values that you may actually see if you actually did an experiment, but they do help make this point. So I'm going to say that TH is going to be 800 Kelvin. So this is the average hot temperature of the red block. And the average cold temperature of the blue block is going to be 200 Kelvin. So I'm just making up some values here just so that we can kind of see how this works out. Now I'm making up this bogus value here that the value of Q, the heat lost by the red object and gained by the blue object, is going to be equal to 100 joules. And I'm going to tell you that the entropy of the system initially starts at 8 joules per Kelvin. Now, I want to make sure that you understand that these numbers do not relate to one another as you could actually calculate out an entire system, but we're just using them to make the point here that SFS will always be greater than S initial S. So let me go ahead and plug in some of these values here. So I'm going to say that this whole thing started at a value of 8. The heat flow out was 100 joules divided by the starting temperature of the the average temperature of the hot object at 800 plus the 100 joules that was gained by the cold object divided by its average temperature, which I defined as 200 Kelvin. So let's do a little simplification here. So we have 8 minus 1 over 8 plus 1 over 2. You can see here that this value over here, this fraction, will always end up being a bigger fraction or a larger value than this one would over here, because this value is always going to have a smaller denominator, having started at a lower temperature and therefore have a lower average temperature. So let's go ahead and get a common denominator here. This is going to be, we could do 64 over 8 minus 1/8 plus 4/8, and if we calculate that out, we've got 63/8 plus 4/8 would give us 67/8. Now this value, the initial entropy of the system was 64 over 8, and the final entropy of the system is 67 over 8. And you can see that there has been a change in the entropy, that has been an increase. So what we're saying here is that SFS will always have to be bigger than S0S, because these fractions, this first fraction over here, is always going to be a smaller number than this fraction over here. And so the fact that if heat flows spontaneously from a hot object to a cold object, the entropy of the system always has to end up bigger, because this fraction the ratio of the amount of heat gained to the average temperature of the cold is always a bigger value than this one. And you can try out any numbers you want, as long as TH is bigger than TC, which is what's required for there to be a spontaneous reaction, you can never get a larger answer to this problem than we did with what we started with. So this is just a way to show that the final entropy of the entire system will always end up being bigger than the initial entropy. The other possibility is that it could be zero in a reversible process, but it can never have decreased over time. Now, the last thing I will leave you with is to think about this. The entropy of the hot object was lowered in this process. The entropy of the cold object was increased, but the entropy of the system always ended up being a bigger value than either of the initial values had begun with. So it's really important to note that the entropy of an object in the system here can have decreased, but the entropy of the system as a whole will never decrease. It will always increase or remain the same.